most complete connected Riemannian manifold with no negative Ricci. And assume that it contains a line. So what it is a line is a geodesic parameterized on the bool R. It's, if you want, it's an isometric embedding of R into your space. That, I mean, already Tapio mentioned this in his talk. So it is a curve such that for any t and s, the distance between gamma t and gamma s is t minus s in absolute value. So that's a line. Then what happens in this case? Well, in this case, your manifold is a product manifold of that line times, say, an orthogonal manifold in some sense. What's the best way to see this theorem? Well, for me, it's look at dimension 2. Take a surface. And for a surface, all the curvatures are the same. Sectional, Ricci, Gauss, scalar, whatever. So that's easier. And now we have a clear picture of what is a surface with a non-negative curvature, right? It's sort of bumping like a sphere, not like a saddle. And now, if such a surface as a line, well, it is either the plane or the cylinder. Nothing else. Because it is a line cross a one-dimensional manifold, which can be either R or S1. I mean, there's nothing else left. Okay? So why is that the case? Well, because essentially from every other point of your surface, it should pass a line which is parallel to the given one. That's the heuristic idea behind the proof. Because if not, then you create a saddle point. Now, this is a statement like the splitting is what is called the rigidity theorem. So a rigidity theorem is like identifying the equality case in an inequality. Typically, when you have an inequality, in the equality case, you have some special structure, right? I mean, I know Cauchy's bars. If you have equality Cauchy's bars, then the vectors must be parallel. If you have equality in order, then the function must be 1 the power of the other up to constant. And why is this sort of the same idea? Well, the point is, if you have a manifold with a Ricci bounded from below by a positive constant, then there's a theorem due to Bonnet and Myers that tells that the diameter is bounded. The diameter is at most the diameter of the sphere with the same dimension and same lower Ricci bound. So if you have a manifold with a positive lower Ricci bound, you cannot find a line in it because the diameter is bounded. Now, so in some sense, now lower your Ricci bound. Ricci bound greater or equal than 0 is the first case where you might have a line. Okay, and asking for the presence of that line is a sort of, asking for this maximal situation. Okay, and in this case, well, you must split. You are that line times another manifold. So that's the classical splitting theorem. And then a sort of sharper version of this theorem is what is called the almost splitting. And I must say I got confused for a while by this name, because the almost splitting is more powerful than the splitting. And the almost splitting tells basically this. It's a quantitative version of the splitting. I mean, the true statement is very long, but heuristically it says this. If the hypotheses of the splitting are almost satisfied, then your thesis is almost satisfied. So if your manifold maybe has not a negative Ricci, but there's Ricci bounded from below by minus epsilon with epsilon small. And you have a geodesic which maybe is not really a line, but is very long. Well, then there is a big portion of the manifold around a ball centered in the midpoint of your geodesic, which maybe is not a product, but close to be a product in the Gromov-Hausdorff sense. Distance minimizing, absolutely. No. If it is not compact, must contain geodesic arbitrarily long, and then the existence of rays. Then of course you can speak. You can say that again.
If there's a line, then it's split. So very, very few have lines. And if there's a long geodesic, the middle of the geodesic almost split.
Yeah, exactly. So can you apply this theorem and then reduce that big portion of the space?
Under which assumption, sorry?
If you have a complete non-compact and there's a ray, and it has small diameter drop, then you can get this ball around the ray to be big enough to cover parts. So if there's sublinear diameter drop, you can get so that around the ray you
I didn't get the question. Sorry. I mean, what's your question? Okay. Mm-hmm. Yes. Yes. Yes, you can. I mean, that's so. So the point is this. So a good point of the almost split. So let me. I mean, a typical application of the almost splitting is the following: take any space with Ricci curvature bounded from below, maybe by -100, and now take a geodesic, maybe very small, okay? And now blow it up, multiply your distances by 1,000. So scale the space. Are you with me? So if you scale, so the point is, if you take a space with Ricci curvature bounded from below by some constant, then you multiply, I mean, the distances by you scale the distance by some factor, then what was a priori a bound from below by -1,000 becomes, you say the lower bound approaches 0. And what was a small geodesic becomes a long geodesic. So now in this region, close to the center of the geodesic, you almost split. So in fact, the almost splitting also tells you something about the local structure of in fact, we will see later some consequences in this sense. Okay. Let me point out one thing, that this almost splitting implies is a one-line argument, implies the splitting for rich limit spaces. So take a space which is everything fine there? Fair enough. So Gromov-Hausdorff or measure Gromov, fair enough. So but Gromov-Hausdorff and measure Gromov-Hausdorff is essentially the same under doubling condition. So if you are Gromov-Hausdorff close and all your measures are doubling, then up to taking subsequences, you must be also measure Gromov-Hausdorff close. So fair enough, but it is locally. I mean, the local. So if you take a ball of radius 1, you are working on a given. I mean, when you speak about you're right. I mean, I didn't specify the notion which is behind it is more or less the same that Tapio pointed out of pointed measure Gromov-Hausdorff convergence or pointed Gromov-Hausdorff convergence, which requires essentially Gromov-Hausdorff or measure Gromov-Hausdorff convergence on balls over every radius. You fix a radius and the balls are converging. And now on given balls, your measures are doubling. And now when you have doubling measures, the difference between Gromov-Hausdorff and measure Gromov-Hausdorff is not that much. Okay. Now, sorry, Emmanuel, Christian, there's no, you can speak, but it's lower, a little bit lower volume, please, because you can. So the almost splitting implies the splitting for limit spaces. So namely, if you have a space which arises a measure Gromov-Hausdorff limit of a sequence of Riemannian manifolds with a certain lower Ricci bound, which is going to 0, a certain given upper dimension bounded, and the presence of longer and longer geodesics. Okay, so okay, assume that your limit space contains a line, then a space. So that's the point. So you get the splitting not only for smooth manifolds, but also for guys which are limits of smooth manifolds. Okay, and why? Well, essentially, because if the limit space contains a line, it means that the approximating spaces must contain longer and longer lines. And the lower Ricci bound is going to 0, so bigger and bigger portion of the approximating space should be close to product, and therefore the limit to your product. Now, an interesting fact, which is a consequence of Gromov precompactness theorem, is that actually if you know just this guy, then you can deduce the almost splitting. Why? Because, well, suppose not, by contradiction. So so suppose the almost splitting is false. Then you should be able to find a sequence of Riemannian manifolds with a certain given upper dimension bound, whose lower Ricci bound is going to 0, having longer and longer geodesics, but which are not closer and closer to a product around the center of the geodesic. Well, But by Gromov precompactness theorem, such a sequence would have a subsequence converging to a limit space in the measure Gromov-Hausdorff sense, converging to a limit x. And that limit x should contain a line, because those approximating manifolds have longer and longer geodesics. But so this limit x splits, thanks to the splitting for limit spaces. But so we find a contradiction, right? I mean, our manifolds were converging to this x splits, so big portions of our manifold must split. Okay? So in fact, this and that are more or less the same, I mean, more or less the same statement. I'm cheating a bit in the sense that the statement of Chigger and Kolding, sorry? Yeah, that's what I was going to say. So the statement of Chigger and Kolding, of course, comes quantitative, while this compactness argument does not give you any quantification. But on the other hand, frankly, the quantitative statement per se, I mean, the precise quantification is not that relevant, right? I mean, you just have, I mean, in applications of the almost splitting is not that relevant. So yeah.
I don't understand how one gets this for x, because
so the implication from
they don't contain line. I mean,
from top to bottom, you mean?
Yeah, I mean, so the Riemannian manifolds, do they contain a line? I mean,
So assume that the limit space contains a line. If the limit space contains a line and you have a space which is Gromov-Hausdorff close to that space, you must contain a long geodesic. So if you are converging in the pointed Gromov-Hausdorff sense, okay, okay. Very well. Now, of course, the question is whether we have the splitting for RCD, and we have. So that's the statement. Notice that just for CD, well, let me say the statement. So the theorem is the following. So pick an RCD zero-n space, assume it contains a line. That's a purely metric notion. Well, then the space is isomorphic to the product of another space times the real line R, where of course the product distance is the one given by Pythagoras theorem in the metric setting. And your quotient space is, well, RCD 0 and -1, whenever this makes sense, or a point if your initial dimension was too small. And notice that on the class of CD without the R, the class of CD, this statement is trivially false. Pick R2 with a norm. R2 with a norm, Pythagoras theorem does not hold. So I mean, it contains a lot of lines. It's CD 0n, but it doesn't split. Okay, so of course, in particular, this provides a non-quantitative version of, I mean, in particular, this applies to Ricci limit spaces, and so provides a non-quantitative version of the almost splitting. So in this sense, it's a generalization, but not quantitative. It provides some information about the quotient space. In the almost splitting theorem, there's basically no information about who is the quotient space besides being a geodesic space. Now you know that the quotient space, you can pick it to be RCD 0 and -1. Please, Emmanuel. This one? Please. No, I was not going to say anything. What do you want to know? Yeah. If it contains a line, then it is a line. There's no space to be anything else. Precisely, and this in fact gives the strong information, by the way. I mean, we will see some. I mean, these rectifiability results that Tapio told about, I mean, it is an elaboration of this fact. Precisely. And at the end, I mean, you are in a range where you must be just a point.
It's not known whether actually all these RCD spaces always have to have an integer dimension, constant,
the constant dimension, integer. So okay. So we need to understand what is the dimension. So the dimension of the tangent space, it's no, I mean, tangent space knows to be almost everywhere RD, but D can depend on X. Yeah. And that's it. But I mean, the fact that D is an integer is essentially, yeah, I mean, a consequence of this. That this between, I mean, that's the root of the result is there. Okay. Okay. But this is not, I mean, this is not hard to believe. Take an RC. So the point is that the Hausdorff dimension, this is known and it is easy. The Hausdorff dimension of an RCD Kn space is less or equal than n. Now if you have an RCD, I mean 0n with n strictly less than 2 space, which contains a line, what else can it contain? I mean, it splits, so it's a product of a line and something else. I mean, if that something else is more than a point, you have Hausdorff dimension 2, right? I mean, you see what I mean? So that can be. So you're aligned. Okay. What? If you are a product, and your quotient space is also RCD, I mean, an RCD space is geodesic, right? So it has Hausdorff dimension at least either 0 or 1, right? Or more than 1. Now, take that across R. That is either 1 or more than 2. I mean, but there can be anything between 1 and 2, strictly between 1 and 2. You see what I mean? The measure is the product measure. So I'm making a very simple statement. So forget about everything. So take an RCD space. So either that space is at one point, or there is a non-trivial geodesic somewhere in there. The condition is given by geodesic convexity of entropy. So either all geodesics are trivial, or there is a non-trivial geodesic. Now take that space and multiply by R. What is the Hausdorff dimension that you get? Is at least 2. And now, but the Hausdorff dimension must be bounded from above by that n on an RCD 0n space. That's by a covering argument. Essentially, there's a matter of something that has to do with the doubling constant of this space. End of the proof. Okay, so that's the easy part. And the harder part is to show that there is this geometric result about the splitting. So let me tell you how the proof goes in the classical case, and then we see how to adapt. How we can use our arguments to make the proof in the non-smooth case. So everything evolves around the study of this so-called Busemann function. So the Busemann function is this. So consider a ray. A ray is just an half-line. So a geodesic parameterized ray on positive reals. Right? Now I want to consider the function essentially minus the distance from the point to infinity. Which of course makes no sense because point to infinity is not a point, but what I can do is that I can take the limit when t goes to infinity of that difference. Okay, t minus that distance. And that limit exists because in fact it's a soup. This is a consequence of triangle inequality. That's easy to check. If that was a geodesic, that's easy to check. Now, actually, of course, if we have a line, so you have two rays, you can either take t goes to plus infinity or to minus infinity, and you get two Busemann functions, distance from one point and distance from the other end point in some sense. And now the point. So what has Ricci in a negative to do with the Busemann function? The point is that if you recall the Laplacian comparison estimate for the square distance that we have seen yesterday, then you see that up to a chain rule, you get that the Laplacian of the distance is less or equal than the dimension divided by the distance from the point that you fixed. That's for any t. Now, if you let t go to infinity, the Busemann function is sort of limit of t minus distance to gamma t. Take the Laplacian of this guy. The t disappears. There's a minus changes the guy, and this gamma t was going to plus infinity, so you get the Laplacian of the Busemann of an half ray is non-negative. Of course, there is something to justify in passing to limit, but that's sort of the idea. Okay. So the Busemann function associated to a ray is subharmonic. Looks like that. There's a non-negative Laplacian. But now what's the point? The point is that now take these two Busemann functions associated to your line. Now both are subharmonic, so their sum is subharmonic, right? So the Laplacian of b plus b minus must be greater or equal than 0 because the Laplacian is linear. On the other hand, by the triangle inequality, that's just triangle inequality. So you have that the sum. So imagine. So this is your picture. This is your line. This is your point x. Now this is gamma t. This is say gamma minus t. And of course, the distance from x to gamma t plus the distance from x to gamma minus t minus 2t. That's that has a sign. It's a positive, right? So the Busemann function, the sum of the Busemann function is the opposite of this sum, so it has a sign, right? So you let t go to plus infinity, and you get that the b plus b minus is always less or equal than 0, but on the line it is 0. On the line you have equality, right? And now something is happening, right? We have a function of this shape which has a maximum, so it must be constant. That's the strong maximum principle. If you have a function with a non-negative Laplacian, which has a maximum in the interior point of your set where you are looking at it, then it must be constant on the connected component, so everywhere. Okay? So it is constant, and in particular, both B plus and B minus, so these are harmonic, right? Because now, I mean, there's no room for having a negative Laplacian, given that, I mean, they're constant. Okay? I mean, the sum is constant. Now here it comes Bochner identity. So the first equality over there is the identity that I didn't want to write yesterday, so that's called Bochner identity. So in every Riemannian manifold, for every smooth function, the Laplacian of grad f squared is equal to the Hessian squared of f plus grad f grad Laplacian f plus the Ricci curvature in the direction grad f grad f. That's just a computation. Huh? On RD, you will not have the last term. Huh? On a Riemannian manifold, the curvature appears, and the correct term is that one. Okay? Now, if our manifold has no negative Ricci, I can drop the last term and get greater or equal than the rest. And moreover, if I apply Cauchy-Schwarz, I know that the Hessian of f squared, the Hilbert-Schmidt norm, squared is bounded from below by the Laplacian of f squared, by the trace of the Hessian, which is the Laplacian, squared divided by the dimension. That's Cauchy-Schwarz. Equality holds if and only if the Hessian is a multiple of the identity. Okay? And now what's the point? The point is that I apply this to my Busemann function, either B plus or B minus. That's the same, so say B plus. Now, the Busemann function, you can check it as gradient, which is identically 1. It's a sort of a limit on one Lipschitz functions, which, I mean, remains one Lipschitz. You don't, I mean, that's not hard to check. The gradient is really 1. And the Laplacian is 0, right? So what do we have? We have the Laplacian of 1, that is 0. And on the other hand, we have, so Laplacian of B is 0 plus grad B, whatever it is, grad Laplacian, this is also 0. So we have equality over there. So for the Busemann function, we didn't lose anything in passing from the Hessian to the Laplacian squared over dimension in doing Cauchy-Schwarz. So the Hessian is 0, right? I mean, it cannot be bigger than 0. So this means that this function B plus is both convex and concave along geodesics. And well, what do we do now? Well, now, given that this function B plus is convex, you take its gradient flow, it must contract distances, right? The gradient flow of a convex function is something which decreases distance. But this function is also concave, so its gradient flow should increase distance. But so the gradient flow of this is one parameter group of isometries, right? Because it is both convex and concave, this function. And now you see where the parallel lines to our initial line are coming from. They are the orbits of every other point in the manifold through this gradient flow. And we are drawing a lot of lines in our manifold. And now how to conclude now? Well, who will be your quotient manifold will be a level set of our Busemann function. So take B equals 0. And well, now it's more a matter of basic differential geometry. You take a point in this submanifold and a tangent vector, then it is sort of trivial that this tangent vector times the gradient of B is 0 because this tangent vector, I mean, it goes in the direction where B is constant. So this is 0. And well, now you're done. I mean, that's essentially what is telling you that your M, I mean, the tangent space at x of M splits as the tangent space of N times R. That's basically the content of this guy. It's a matter of writing down a little bit more carefully the fact, but that's the point. So let's try to do the same in the notebook case. We require more work. I mean, it's not as easy as the Abel-Scrum model that you sort of copy-paste. This requires some new idea. And so here they are. So first of all, we've seen yesterday that we do have Laplacian comparison estimates even in these spaces. So, I mean, by sort of the same things that we do in the smooth case, we do obtain that the Busemann function is subharmonic. I mean, both the Busemann functions. So the Busemann function is a purely metric object. So that limit of t minus distance x gamma t, that's a purely metric thing. So that is well defined. And they are subharmonic. And actually, the strong maximum principle holds even in metric measure spaces. You need some assumption. You need a doubling condition and what is called the weak local 1-2 Poincare inequality, which is there on RCD zero-end spaces. So elliptic regularity theory, in some sense, is in place in these spaces. So Harnack inequality are there, and the strong maximum principle is there. And for what it matters to us, we can deduce that the Busemann functions are harmonic. Okay. So there we are. And now what do we do? Now I would like, now I'm a bit in trouble with, so I know that the Busemann function are harmonic, I know that the gradient is 1 in whatever sense, but I don't have Bochner identity. At the time of proving the splitting, I didn't have even the Hessian, I mean, we have to find a way to sort of get around this problem, even in the smooth setting if you want. And perhaps one intermediate step is to try to show that the gradient flow of this Busemann function exists and produces a parameter of measure preserving maps, a family of measure preserving maps. If you have an harmonic function on RD or an Riemannian manifold, this gradient flow preserves the measure. I mean, more generally, if you have a divergence-free vector field, its flow will preserve the measure. Now, take as vector field the gradient of an harmonic function, which is divergence-free, and this flow should preserve the measure, right? So let's try, first of all, to fix this. I mean, in the not-smooth setting, we need to keep careful track even of the measure. I mean, in the smooth one, you can sort of sometimes do not pay too much attention, but in the not-smooth setting, you have. And now here there is a sort of a new insight. And the fact is that for whatever real number t times the Busemann function is C concave. And I can tell you who is the C transform. I mean, it's given by the sort of the other Busemann function plus or minus something. So one remark on RD, if a function is such that whatever its real multiple is C concave, then the function must be affine. There's no other choice. So this claim about the C concavity of the function t times Busemann for whatever real t is a quite strong rigidity statement. And the idea for this is the following. So what is a C concave function? A C concave function is a function whose graph, I mean, is like the inf of a family of distance squared over 2 kind of functions, right? So if I can draw the graph of my function by distance squared from a certain point plus a constant, then my graph will be C concave, right? So that's sort of the definition of C concavity. And now the point is that the distance function from one single point will never be C concave because I cannot draw, I mean, I cannot reach sort of the vertex with parabolas. I mean, there's a corner here. But as far as I'm sort of away, I mean, the distance from my vertex is more than 1. I mean, beside that point, I mean, I can draw, I mean, there are parabolas here. That's sort of the geometric picture. So I can draw all the graph of a distance function except what is close to the vertex. But for what matters, the Busemann function, this vertex is going to plus infinity. So I won't say it. So the Busemann function is C concave. That's basically the point. Okay? And its opposite is C concave, its multiples are C concave, etc., etc., etc. So that's an observation. And no. In the sense of optimal transport C concavity. So a function is C concave. So phi is C concave. If there exists a function psi such that phi of x, but thanks, I mean, took this for granted. So it's the infimum over y of distance squared xy over 2 minus psi of y. That's the definition of C concavity. If I can find C is not a constant. It's the cost. And cost is distance squared. Sorry? Precisely. It's a kind of, yeah, that's where, so it's concave with respect to the cost function C. If you are on RD and Cxy is the scalar product of xy, this is concavity. There's no constant. No, that's a cost. It's another life. I know. This is another life. Yeah, no. It has nothing. So this is a no. It's nothing to do with barriers because this is a global condition. Okay. So like concavity is a global condition. Now, concavity you can read by differential terms, but this you cannot. There's no, it's not a differential inequality. This is really something which either holds or does not. Okay. So if you look at the definition, maybe now it's more clear what I was saying. So you can draw for a secant-k function, you can draw the graph by taking inf of distance squared from some points, and then the height of the parabola is that psi or minus psi. Right? Now, why I'm happy about that? Well, because now optimal transport comes into play, and RCD condition, have to do with optimal transport. So maybe I can do some use of it. And the point is that now from the theorem about the existence and uniqueness of optimal maps that I discussed yesterday, we can say that for almost every x, you have only one y. There is only one point, ft of x, which belongs in the C subdifferential. So what is this C subdifferential? So you have a secant-k function. So the point is this: you have your secant-k function. Now, so the graph. The graph of this function is sort of the envelope of inf of parabolas, right? Now, if you sit at a point x and you look at the vertex y of the parabola, which is touching the graph from above, now this y is said to belong to the C subdifferential of this convex function. That's the definition. Okay. And now the point is that if you there's a basic statement of optimal transport is that whenever you have a plan, a measure of the product space, which is concentrated on set of points such that y is in the C subdifferential of x, then the plan must be optimal. Okay, that's an if and only if. Now this in particular implies that whenever I have a secant-k function, take my secant-k function, and let's pretend that for a positive set of x, I can find more than one y, such that this is true. Such that I can touch from a parabola with vertex in y the graph of x. Then I could produce an optimal plan, which sends points in two different directions for a set of positive mass. But this can't be, because every optimal plan is induced by a map. Optimal plan must be induced by a map if the starting measure is absolutely continuous. So this means that for almost every point, you can. That's true for whatever secant-k function on RCD space. For almost every point, there is at most one guy, actually exactly one guy. But so in the statement that existence of uniqueness of optimal maps. So yesterday, I told that there's this result of Tapio, Sturm, and myself, telling that if you have two measures on an RCD, probability measures, and the first is absolutely continuous, the second doesn't matter, but the first is absolute, then you only have one optimal plan, and this optimal plan is induced by a map. Right? So I can rephrase this by saying that every secant-k function on RCD is such that for almost every point there is only one y in the C subdifferential. That's sort of the same, right? And that's what I'm saying here. And let me call that point ft of x because we'll depend also on t, right? And now it's not hard to check that. Actually, for almost every x, the map which takes t and gives back ftx is a line, and that this composition rules. That's really not hard. And moreover, so this in some sense is a way of building the gradient flow of B in a setting where standard techniques do not apply. By luck, that function B is also secant. All its multiples are secant-k, and this ft ftx would be the gradient flow starting from x if I were in this smooth case. I didn't know how to build a gradient flow by standard means, but this one sort of is a help. This trick of passing through the secant cavity and optimal maps. And now the point is that now fix an absolutely continuous measure mu equal rho m, and look at the map which takes t and gives back ft push over mu. Now that's in fact is a Bernstein geodesic induced by the Kantorovich potential Busemann function, sort of by construction. And now if you look at the proof of the Laplacian comparison estimate that I showed you yesterday, and arguing like that, you see that this this ratio must be, that's a sign. So the energy, the Renyi type energy at time t must be bigger than the Rayleigh type energy at time 0, because the Laplacian of B is greater or equal than 0. That's sort of how the subharmonicity of B comes into play in here. So the Rayleigh entropy of this pushover must be greater or equal than the initial one, but this is a group. I can sort of invert time and go back. And so actually I must have this, so that the Rayleigh entropy of this Ft pushover mu must be equal to the Rayleigh entropy of mu. But this being true for any mu means that this pushover, if I have a map which doesn't change the Rayleigh entropy of any measure, that map must be measure preserving. There's no other choice. If it was concentrating, I could sort of pick a measure where the mass is concentrating and get a different Rayleigh entropy. Sure. The first? No, wait a second. So this is not the definition. This is the computation that I showed yesterday about the Laplacian comparison estimate. So the derivative, let me put this way, the derivative of the Rayleigh entropy at time 0 along the geodesic is governed by the Laplacian of the Kantorovich potential. Precisely. Below, okay. I'm not sure. Okay, well, anyway, so I believe. I just don't know. So if you remember yesterday, when I was differentiating at time 0 the entropy, I was getting something like this. Now, what I'm saying is this. So you can do it the following way. So the derivative of this Rayleigh entropy along a geodesic governed by a subharmonic Kantorovich potential must be positive. Okay. Now, this mu t is a geodesic governed by a Kantorovich potential, so the derivative of the entropy must be positive. But if I go backward, I'm also subharmonic, because there is some rigidity in here going on, and you have to play with derivatives and be sure that you can integrate properly things. But the idea is that I should increase the entropy both going there and going there. So in fact, my entropy must be constant, okay, for whatever measure mu. And so this means that my map cannot concentrate measure. Okay, so this must hold. And now about Bochner inequality. Now here we need something, because so in the smooth case what you use is the Bochner identity, and then the inequality you check that you have equality of the first and last terms to force the equality in the Cauchy bars. Now here we don't have at least yet an Hessian, and we don't have Bochner identity at least yet, and so we have to do something else. So that's all was present when the time of writing the splitting. So how can we get the same information about the Hessian just by this inequality and the Hessian of the Busemann function? We have this inequality in some weak form. Then let's pretend we are in a smooth case, but we only know this, and we are not allowed to use Hessian or Ricci curvature. How can we play with this inequality to get an information on the sort of non-existing Hessian? Well, the point is to observe that for the Busemann function, we do have equality, right? For the Busemann function, we do have the Laplacian of the gradient square is 0, because the gradient square is constant, and the Laplacian is 0, right? And so the two terms are cancelled. So in a sense, the Busemann function is a minimum you can write the Euler equation, right? So write this inequality over there for Busemann function plus epsilon your preferred f. Expand. And so the terms with just the Busemann function will simplify. You will get some terms with epsilon squared, which will not matter. And with terms with epsilon, well, this. And of course, you get an equality because you can take epsilon positive or negative. You are free to take. Okay? So now, notice that on the smooth setting, if you take, you expand the left-hand side and you subtract the right-hand one, what you obtain, so it's worth to point out that the Laplacian of grad B, grad f, minus grad B, grad Laplacian f for an harmonic function, this is equal to the Hessian of B, scalar product Hessian of f, plus the Ricci curvature in the direction of grad B, grad f. That's an identity. Now, if you know that this guy is 0, given B, this guy is 0 for every f, you see that this implies that the Hessian of B must be 0, and the Ricci curvature in the direction of grad B must be 0. Because for your preferred point, for any given vector, and then give a symmetric matrix, you can find a function with that vector as gradient and that symmetric matrix as Hessian. So if this is everywhere 0 for whatever smooth f, you must recover the same information about the Busemann that you had in the smooth case. So that's a way of writing that the Hessian of B is 0 even if we don't have an Hessian. And now, how can we use this information to go on with the proof of the splitting? The idea is the following. If you take a function f and you differentiate the Dirichlet energy of f composed our flow ft, and you apply that formula, what you obtain is that this derivative is 0. It is tricky to do this derivative in the non-smooth setting because you have quite many things to check about the differentiability of the derivative. But let's presume that in the smooth world, this is what you get. So in other words, what you deduce is that the Dirichlet energy is constant along the flow. So pick a function, compose it with your ft, and the Dirichlet energy doesn't change. Now in the smooth world, this already implies that the gradient of ft must be the identity at every point. So that ft must be an isometry. In the non-smooth world, for the moment, we still have a regularity information at the level of Sobolev functions. Now I would like now I would like to turn this information to saying, look, this ft is really an isometry, as a measure preserving isometry. And how do I do? And here there is an interesting duality statement, which I first present in the case of metric spaces, and then to point out to you an analogy. I take two metric spaces and pick a map which is invertible. Then this map is an isometry if and only if it preserves the Lipschitz constant of real valued Lipschitz functions. If and only if. That's, one implication is trivial. If it is an isometry, then Lipschitz constant do not change. But on the other hand, the distance is the dual object of Lipschitz constant, right? The distance between x and y, say, is the sup of f of x minus f of y among all one Lipschitz f, right? So you can recover. So if I give you a set and I tell you, look, for every real value function, this is the Lipschitz constant, then you can recover the distance, right? So if you have, so that is true. And now there's an analogous statement for metric measure spaces with low Ricci curvature bound. So pick two metric measure spaces which are RCD k infinity. Pick a map which is Borel invertible, at least almost everywhere. Then the following are equivalent. T is, after modification on a negligible set, an isomorphism, so a measure preserving isometry on a metric measure space, if and only if it preserves the Sobolev normal functions. So that's sort of the analogous of the statement in a way which takes into account also the measure. And notice that here some regularity, a priori regularity information on the space is needed. Without this, for general metric measure space, this is just false. Simply because on a bad metric measure space, Sobolev functions they are not rich enough to characterize the geometry of the space. But on RCD k infinity spaces, this is the case. Okay, so you have an isometry by duality, and now we are done, right? Because we had a map which was measure preserving, so the L2 part of the norm linear is preserved, and was preserved the Dirichlet energy. So even the gradient part was preserved. So our maps FT satisfy this. So up to modifying them on a negligible set, there must be isometries, right? And now you can define the quotient space, right? So you can say that x is equivalent to y if they lie on the same orbit, right? And now you can sort of so on this quotient space x prime, you put a distance d prime, which is just the inf of the distances that you can see on the orbit. So that's the standard quotient distance that you put on a quotient space, right? And what is the measure that you would like to put on your quotient space? Well, you would like to say, well, I pick a Borel set in my quotient space, I lift it up with height 1, and then I look at the measure of that sort of strip in the original space. So that's what you do. So you take its inverse image with respect to the projection, you intersect it with the strip of height 1, and thing which is totally non-trivial. So notice that, there is a natural immersion of this quotient space in your original space. You can say that the image of a point x prime is x if this x projects on x prime, and say you are at the level 0 of the Busemann function. Now, what is trivial is that this map is what? I mean, expands the distances, right, of 1. But the problem is this is an isometry. I mean, so does this quotient space isometrically embed in your original space? So I don't know if the question is clear. Imagine on a smooth world, you have a function. You take a smooth function. Say you take the 0 level set, say that made of regular points whatsoever, and now you want to know whether, I mean, you have a Riemannian manifold, you have the Riemannian distance, and you want to know whether the Riemannian distance computed in the ambient manifold is the same as the Riemannian distance computed in your submanifold. I mean, if it is totally geodesic or not, that's the question, right? Or maybe if there is a shorter path connecting points which goes far. Of course, in the standard splitting, this is the case, at least a posteriori, right? If you are n cross r, then n sits as a totally geodesic submanifold, right? But in this non-smooth case, things are a bit trickier because, I mean, it is hard. I mean, it will be hard to prove that x is the product of x prime cross r if we don't have some regularity information on x prime a priori. So because we don't know how to put our hands on x prime. And the best information that we can hope for is that x prime is also RCD something. And this essentially can only come if we are able to prove this in isometry. Okay? So how can we do that? So the point is this. Is an isometry, it means proving. So this is the picture. We have x, which is sort of fibrated by all of these lines, and we have x prime, which is our Bochner space. And now I pick a point, which is, so this is b equals 0, if you want. Now I pick a point in here, and what I want to know is whether the minimum of the distance from this point and the point on a given orbit lies when t is 0, which is a quite primitive version of Pythagoras theorem, right? I mean, by Pythagoras, after I know the splitting, I know that the distance between this guy and this guy will be equal to this squared plus this square root. So asking that this is the minimal distance is a sort of very primitive version of Pythagoras, which still is quite hard to prove. And why this is hard to prove? Because, well, I know that the minimum exists, because if I go up or if I go down, I go to plus infinity, so by compactness the minimum exists. Now we'll have to take the Euler equation of this minimum. But of course, for given, say, x and say y in here, the function will take t and gives the distance, say, even squared, if you want, between ft, y, and x. I know that this is Lipschitz. I have no idea whether it is C1. For what I know, it can have a corner in the minimum, and I'm really not able to gather information. But the point is that we can get C1 regularity. And the idea is we don't do analysis on points, we do analysis on probability measures. So we lift the analysis. And so I don't study points, pick whatever Wasserstein geodesic made of measures with uniformly bounded densities. Okay? And take a family of Kantorovich potentials, say from an intermediate measure to the target measure, appropriately scaled. Now the interesting fact is that if you take a Sobolev function and you look at the map which takes t and gives back the integral of f in d mu t, now this is not just Sobolev, this is not just Lipschitz, this is C1. It is C1, and this derivative I can tell you is this derivative at any time, and this is this. So that's a way of saying that mu t satisfies the continuity equation with a vector field grad phi t. Imagine you are on a smooth manifold. What I'm saying is that dt mu t plus the divergence of grad phi t mu t is 0, right? That's the distributional version of this guy. So what I'm doing, I'm writing the continuity equation on metric measure spaces to get this C1 regularity. And now the point is that it is plenty of geodesics of that kind. So on our metric measure spaces, we have plenty of C1 functions. Now you apply this argument to the geodesic, which is so here. Now, rather than take one point and try to minimize the distance square, you take a measure, and you perturbate the measure up and down with these flows, and you look at the Wärtsilä distance through the delta. And now this function will be C1. Now, in the minimum, we will have zero gradient, and now you can run your analysis. Yeah, I mean, sorry, I forgot. So also the square the Wärtsilä distance is C1, and you have an explicit formula for its derivative. Now, if you are confused by this formula, well, that's just the same formula that is there on RD. That's the very same formula. And yeah, sorry? Okay. So you can run your computation, deduce the Euler equation, so deduce that at the minimum of this distance squared of ft push over mu and nu, you must have this, this identity. So fix a measure, nu, pick another measure mu, and perturb it along your gradient flow. And ask, where will I achieve the minimal distance Wärtsilä squared? Well, at that time, such that sort of the height, so the integral of the Busemann function is the same, right? And now that you have established that, you can let your measure, the support of that measure, go to points, and now you deduce that now, say you do the same result when mu and nu are deltas in a sense, and so the delta is so the minimum is achieved where the Busemann function is the same, and then now that the space isometrically embeds, you get now it's easy to see that this is an RCD 0n space. With a priori, you still didn't get any dimensional reduction, still the same n. But now most is done. What remains to show, well, that X is isometric to the product, and that this quotient space has one dimension less, or maybe a point if n was small. But that's now the first point again comes. I mean, it's tricky, but again comes from the duality argument with Sobolev functions. So you don't really prove that these are isometric. You rather prove that the natural map from the first to the later preserves the Sobolev normal Sobolev functions. And then you apply again this duality argument that I put it out before. And now the dimension reduction argument, and there's a general trick introduced by Cavalletti and Sturm, which works in this case. I mean, once you know this product structure, that the quotient must be one dimension less, follows by known arguments. So that's it about the splitting. Let me just use the last 5 minutes to tell a couple of words about other geometric results on RCD spaces. So the first is a result by Ketterer, which I simplified. I mean, he proved something more general. Let me state the simplified version is the following. So take a metric measure space, whatever, X, and build a cone over it. Why? So what is a cone over a metric space? Well, a cone is like, so you have a metric space X, so or you take 0 plus infinity cross X as a set, and you quotient identifying, all points with 0, first coordinate, you quotient at a point. And now you put a metric on this space in such a way that, the space looks like a cone. So your X will be the set of points at distance 1 to the vertex. And then you have a lot of scaled copies of X, and there's a formula involving what this metric should be in order for it to look like a true cone. So the point is, if you do the cone over Sn, you get Rn plus 1. Okay, so the cone over S1 is R2. Now this for the metric. If I want to, if I have a metric measure space, I also have to know how do I scale the measure. So let me fix a parameter n and say that the measure of the slice, say at distance r from the vertex, scales like r to the power n. So that's a protruding dimension of my space in a sense. And now what Ketterer proved is that the following are equivalent. So the base space is RCD n minus 1 n, and the cone is RCD 0 n plus 1. So much like this example of sphere and Rn. Okay. A couple of comments. Actually, he proved something more general in the sense that Rather than picking just cones, you could pick here spherical subspensions. So you could decide to scale differently the metric along, say the time direction if you want. So for instance, Sn, you can obtain Sn by warping an Sn minus 1 in an appropriate way. So you let radii goes to 0 in one direction or goes to 0 in the other direction, and if things are properly, I mean, you obtain this sort of constructions. And I mean, there is an analogous version of these theorems where lower Ricci bound other than 0 are there, and with spherical suspension. Yeah. And then you put a sinus to the n. I mean, yeah. Also, the measure has to scale accordingly. Absolutely. No, not just like when you do the spherical suspension, you also have to take into account more complicated version of the scaling of the measure. I mean, the point is that, so again, Sn minus 1 warping 0 pi. I mean, in order to get Sn, you have to scale, the radii, but also the measure in the appropriate way. Absolutely, yes. Yeah. Okay. Now, how did he do? Well, first of all, this result is interesting, even if X is a Riemannian manifold. That is absolutely no, because the point is that a cone typically will have a topological singularity at the vertex. I mean, unless your fiber is a sphere, this vertex will have no neighborhoods homomorphic to RD. So you are telling something about the geometry of a space which is intrinsically not a Riemannian manifold because of bad topological singularities. So. No, but the theorem is true even if you get a singularity. And it's not just a matter of metric, it's a matter of topology. If you take the cone over a torus, here you are messed up. I don't care how you scale the metric, there's a topological issue. Sorry? Is there any way? Sorry? Okay. Well, you can take any manifold with complicated topology. There are manifolds with complicated topology, and then if you shrink. So the point is that it creates. So of course you exit the range of smooth manifolds, but you enter the range of spaces with I mean geometric structures in a way which, by the way, was not really known before. So I mean, these sort of statements are very, very delicate because handling singularity is a mess. That's basically the point. So for instance, nobody knows whether such cones over a manifold can be Ricci limit spaces or not. I mean, you don't really know how to smoothen such a thing. But still, it is an RCD space. And by the way, this is actually probably the only non-trivial way that we have today to produce new Ricci, new spaces with RCD. I mean, rather than the Ricci limits and these constructions, I wouldn't know what else there's there. For Alexandrov spaces, yes. For Alexandrov spaces, yes. You're right. For lower sectional curvature bound, that was known. That's absolutely true. Okay. Now, how did he do? Well, essentially, what he was able to do, I mean, just in one line, because time is almost over. He did everything with Sobolev calculus. So I said that, I mean, if you have a metric measure space yesterday and you know that Bochner inequality is there in some form, then your space must be RCD-Kn, right? Now, I mean, you can do this Bochner analysis in the cone, and it is sort of easy to see that things go well as far as you are say far from the vertex. And the issue is handling the vertex, evidently, and this is very tricky. Let me show you an example why this is tricky. So pick S1. So I said the cone over S1 is R2, right? Now pick S1 with a I mean diameter less than pi, so slightly smaller, and do the cone. And now the cone will look like a cone, right? So this is the product. So this is the cone structure, and this is an Alexandrov space, and so also an RCD space with a negative curvature. Okay, if your circumference is less than 2 pi. Now, what happens? So, because the angle in the vertex essentially is the same as the length of the circumference. Now, what happens if your S1 had circumference greater than 2 pi? Well, you have something which is quite bizarre, because there's a point where the angle at the vertex is more than 2 pi. It's quite difficult to imagine, but the fact is, if you take out that point, your space is flat. It's flat. But with that point on that point, there is a sort of curvature which is minus infinity in just one point. But this means that you cannot check a lower Ricci bound or lower sectional bound staying just far from the corner. So if you write down Bochner inequality for whatever function which is supported far from the vertex, you will see non-negative Ricci because the space is flat. Actually, you will see 0 Ricci. But the vertex is there, and your construction is not an RCD because of this minus infinity. And so he was able to handle that, and so got to get the result. And as an immediate consequence, he got the maximal diameter theorem, so which is another version, if you want, of the splitting, but for positive lower Ricci bound. So I said before that if you have a lower bound on the Ricci, and then your diameter must be bounded, right? And so again, the rigidity question: what happens if I reach my diameter? In the smooth case, that's Chang's theorem. Then you must be the sphere. In the non-smooth case, you know that this can be true. You must be at most a spherical suspension, and that's what it proves. And the idea what it is to combine his theorem with the splitting. So if you had 2 points at maximal diameter at a distance pi, then in the cone, the 2 radii passing through these 2 points would meet up in a line. And the cone would be RCD 0 and minus 1. So now you split. And now your space is sort of the circumference at radius 1. So just very last slide, just one word about the paper by Mondino and neighbors. So that also Tapio mentioned. So essentially, they built Lipschitz charts. So this Lipschitz structure is over there. So that's more or less what they proved. They didn't mention anything about the measure, but I mean, you can prove also this statement about how the measure behaves under these charts. And the point is this: so pick your, and actually it's much better than just Lipschitz. You give me epsilon, and you give them epsilon, and they can find charts whose Lipschitz constant is controlled by 1 plus epsilon. So this is another way of ruling out Finsler type of geometry. So for a normal space, you can find Lipschitz maps through a Euclidean Rn, but you cannot really have that Lipschitz constant close to 1. So that's what they get. And how do they get that? Well, essentially, it's a combination of average Gromol, splitting, and techniques of geometric analysis, which were introduced by I guess, Chigger and Colding in the case of rich limit spaces. So you start picking, you have your space, you pick a geodesic, you blow up in the geodesic, and in the limit you obtain a line. And then RCD 0 in space, so that line splits. And now you start drawing all possible geodesics that you have, and you have a lot of lines, and so your tangent spaces must be Euclidean at almost every point. I mean, this requires some work. And now with some more work, you can show that you must be Lipschitz closed in some sense to your tangent space at almost every point in a way that you can quantify. You don't know, because the only thing that you know, the boundary dimension essentially comes from the splitting that it tells you that you can, take out at most capital N things, and so it's a compactness argument, and that's all there is. So you don't know. It is expected to be constant, but we don't know. Okay, and that's all.